What specific problem does your study address in the context of understanding transformer neural networks?
Our study addresses the problem of limited understanding of how transformer neural networks operate, particularly regarding their reliability and trustworthiness in high-stakes situations. We focus on exploring the specialization of different components within these networks, aiming to identify distinct roles in processing various types of information. By defining modularity in terms of separability and positional locality of components, we investigate how these factors contribute to the overall functionality of the models. Our analysis employs methods like selective pruning and mixture of experts clustering to uncover the relationships between neurons and their respective tasks, thereby providing insights into the emergent structure of trained networks compared to randomly initialized models. Ultimately, our work seeks to enhance interpretability and modularity within transformer architectures, which is crucial for their deployment in critical applications.
How does the proposed method for identifying distinct components within neural networks work? Please illustrate it step by step.
The proposed method for identifying distinct components within neural networks involves several key steps. First, neurons are selected using a scoring method based on the mean absolute deviations between a reference dataset and an unlearned dataset, allowing for the identification of neurons relevant to specific data subsets. Next, the selected neurons are grouped into clusters using a mixture of experts, ification approach where balanced k-means clustering is applied to the input weights of the MLP layers, effectively creating clusters of neurons that are activated simultaneously. Following this, the performance of the models is assessed by selectively pruning neurons associated with specific classes or tasks, observing the impact on overall performance across related classes or tasks. Finally, the overlap of selected neurons between different classes is analyzed to understand the degree of specialization and shared pathways within the network, revealing insights into the modularity of the neural architecture. This systematic approach allows for a clearer understanding of how different components within the neural networks contribute to various tasks.
Can you provide a simple example illustrating the inner workings of your neuron selection process, particularly in relation to the CIFAR datasets?
In our neuron selection process for the CIFAR datasets, we utilize a method akin to selective pruning. For instance, when analyzing the VIT model, we define a reference dataset, CIFAR 100, and an unlearned dataset, CIFAR 20. We score the neurons based on the mean absolute deviations between the activations in these two datasets, allowing us to identify which neurons are most relevant to specific classes. We then select a subset of neurons with the highest scores, aiming for a predetermined drop in top 1 accuracy when these neurons are removed. This approach reveals that neurons associated with similar classes, such as insects and non-insect invertebrates, often overlap significantly, indicating shared neural pathways in the model's processing of these categories.
What are the theoretical advantages of implementing the mixture of experts approach in clustering neurons, and how does this improve model performance?
The mixture of experts, MO approach offers several theoretical advantages in clustering neurons, primarily by grouping neurons that are activated simultaneously, which facilitates efficient expert selection during inference. This clustering allows for a more organized structure within the model, enabling it to leverage specialized subsets of neurons for specific tasks, thereby enhancing performance on those tasks. In our study, we employed balanced k-means clustering on the input weights of MLP layers, which resulted in a clear separation of neurons into distinct clusters, improving the model's ability to process information relevant to different classes or data subsets. The results indicated that pre-trained neurons showed a stronger correspondence with MO clusters compared to randomly initialized neurons, particularly in earlier layers, suggesting that the MO approach helps in maintaining effective specialization and modularity within the network. Overall, this method not only aids in interpretability, but also contributes to improved model performance by optimizing the activation patterns of neurons based on their functional roles.
What metrics or benchmarks did you use to validate the effectiveness of your method, particularly in terms of performance drops in ViT and Mistral models?
To validate the effectiveness of our method, we employed specific performance metrics based on accuracy drops in both the ViT and Mistral models. For the ViT model, we assessed performance across all CIFAR-20 classes by measuring the impact of deactivating neurons associated with particular classes, aiming for an 80% drop in top 1 accuracy. In the case of the Mistral model, we targeted a 20% drop in top 1 next token prediction accuracy for each unlearned text subset, observing correlated performance drops across related tasks. Additionally, we analyzed the overlap of selected neurons between different classes and data subsets, which provided insights into the modularity and specialization of the model components. These metrics collectively demonstrated the effectiveness of our selective pruning method in identifying class-scale features within the models.
What key findings did you report regarding the relationship between unlearning certain classes and the performance drop across related tasks in Mistral?
In our study of the Mistral model, we found that unlearning specific classes through selective pruning often resulted in correlated performance drops across related tasks. For instance, unlearning the biology class led to a significant decrease in performance on the MMLU high school biology task. Additionally, unlearning PubMed Central caused notable drops in various MMLU subjects, including professional medicine and college chemistry. However, we also identified some failure cases, such as Europarl and Freelaw, which had minimal effects on related MMLU topics. These results indicate that while there are strong correlations in performance drops among related tasks, the impact can vary significantly depending on the specific classes involved.